So we want to do this question that says a binary transmission system transmitted with power of that with attenuation of 51 dB and power spectral density of the noise at this level measured in watts per hertz. This signal is to have bit error probability or less than 10 to the power minus 3. So the question is, what is the maximum allowable bit rate measured in kbps for non-coherent FSK? Notice this is not coherent. The key to answering this question is to know how to evaluate the probability of error of non-coherent FSK, which is given by a half exponent of EB over 2 N naught negative, and I would like to remind you that the one for coherent FSK is given by a half Q, which is the error function or complementary error function of EB over 2 N naught square root. So this is a key difference. I know someone may have tried to solve this question using this latter, but the key to answering this question is using that formula. And I'd like to remind you from our notes that is what we found out. I believe we looked at this one, that the probability of error for ASK is given by error function EB over 4N naught. The one for coherent BFSK is given by error function EB over 2N naught. The one we have just illustrated is minus EB over 2N naught, which is the exponent. And the one for BPSK, the one that we looked at, is the half of error function of EB or root EB over N naught. Those are four key equations that we should put in mind, so that whenever we are given a question on probability of error, most of the times it will come from coherent BPSK, non-coherent FSK, coherent FSK, or ASK. The questions we rarely touch on the others, but in the event it does, I believe we should give these equations as well. And now the solution from that equation, we have seen that the power transmitted of that signal is given as 174 milliwatts, which we may express in terms of watts as 0.174 watts. We have also seen that the attenuation is given as 51 dB, which we can express this 10 log of A, which is the attenuation, is going to give us the 51 dB. Whenever A is to base 10, so if you want to evaluate A in terms of power units, this is going to be given by divide both sides by 10, divide both sides by 10, this cancels out, and then this becomes 10 raised to power 5.1 after evaluating this one. This now will give us power in watts. And when we evaluate that, this gives you a number of 125,892.5 watts. And we have evaluated this one at 0.174. You divide by 125,892.5. So remember, the question is asking the maximum bit rate RB. It is asking for the maximum bit rate RB that may be used. So in this context, the question is how do we evaluate this bit rate? Remember, the bit rate is going to be determined by the probability of error that will deliver the probability of error that we are given, PE, for non-coherent FSK, and we are told that the one that we require, it should be less than or equals to 10 to the power minus 3. So we need to be able to evaluate RB. So we need an equation that expresses RB in terms of this probability of error. And we know that we can be able to find the one that we have just shown, that the probability of error, this probability of error is given by 1 over 2 exponent of minus bit energy, or energy per bit, divided by 2 N naught. And we were given earlier, I think I failed to indicate that one, we are given that N naught is 10 to the power minus 14. So because now we know that we are saying that it should be less than or equal to 10 to the power minus 3. This is this equation. So what we also know is that we can also express the power received in a digital communication system as a ratio of bit energy or energy per bit divided by bit duration. This equation is also very important because it gives us the same ratio as this. The power transmitted over the attenuation or correction, what we are getting here is not SNR, is actually power received. The power received is given by PT or power transmitted divided by the attenuation, PT over attenuation. So because we have already found this expression, we need to find power received in terms of EB over TB. And TB1 or TB will give us the reciprocal of RB, which is required. We need the bit rate, and bit rate is always reciprocal of TB. So if we are able to express our power received in terms of EB over TB, then we can be able to evaluate our RB. Since we know this one, we can then say that we can find RB from this. We can actually say here that this is equals to EB RB. So we can now make RB the subject by simply saying that RB, which is the bit rate, will be given by PT or over attenuation divided by EB. So how do we find EB? EB can be expressed from this expression. So if we just equate this to that, just use a different color, we say that we can find EB by multiplying this by 2, then taking the natural log. So we say multiply by 2, multiply by 2, this cancels out, and then you take the natural log of this, ln. So we are saying the ln will cancel out the exponent, and you are going to be left with minus EB divided by 2 N naught is less than or equals to 2 or ln of 2 times 10 to the power minus 3. And if you multiply by 2 N naught, actually divided by negative 2 N naught on both sides, what we will have is that EB, our inequality sign changes sign. When you divide by half, you say that EB must be bigger than or equals to negative 2 N naught multiplied by natural log of 2 times 10 to the power minus 3. So we know what N naught is. We are saying that this should be bigger than minus 2 times 10 to the power minus 14 times natural log of 2 times 10 to the power minus 3. That should be our EB. And when we evaluate this expression, we find that EB should be bigger than or equals to 1.2429 times 10 to the power minus 13. And therefore, for us to find RB therefore must be less than, when we have this sign coming here, we are going to say that this becomes PT attenuation divided by 1 over 1.2429 times 10 to the power minus 13. So we know what this one is. So RB becomes less than 0.174 divided by 125 is 92. You divide again by the value of EB that you have found here. And when you evaluate this calculation, you find that RB should be less than or equals to 1120215 BPS. And when you convert this to BPS, kBPS, you find that the maximum bit rate that is allowed to achieve this bit error rate is 1110.2 kBPS. This becomes our answer, and that is the figure that we find here.